Today, we're going to look at a CPU so powerful that it can pull more than 1,000 watts, making it the first desktop CPU to ever reach those power levels. Or to put it another way, we took a piece of rock, taught it to think, zapped it with electricity, and now it happily puts out a solid mechanical horsepower worth of computation. And not just some lofty peak on liquid nitrogen, we are going to sustain it. All right here today, in Dave's Garage. Hey, I'm Dave. Welcome to my shop. I'm Dave Plummer, a retired software engineer from Microsoft going back to the MS-DOS and Windows 95 days. And today is all about the new champion of the CPU wars, the Threadripper Pro 7995 with 96 cores and 192 threads and 384 megabytes of cache. The chip alone retails for over $10,000 and I'm fortunate to have 3 of them here heating my shop with me. When I heard the new Threadrippers were coming out late last fall, I put the word out that we wanted to get an evaluation system even though it seemed like a long shot for a channel of this size. Well, as they say, it never rains but it pours, and now I'm sitting on 3 of them. One is a serious business productivity workstation, the next is an AI powerhouse, and the third is our 1 horsepower monster. And as you'll see later in the episode, we'll get that one to pull over 1,000 watts under load. I broke out my trusty calculator and that works out to just slightly more than 1.3 shaft horsepower. In stock trim, however, this CPU is limited to 350 watts of total consumption, and that will turn out to be its Achilles heel. Both Dell and HP put out workstations built around this powerhouse of a CPU, and each is a spectacular machine in its own right. Even at its stock limits, the 7995 tops the charts for most important computational tasks. Although AMD EPYC chips exist with 128 cores, they run at a significantly lower maximum clock rate, and so the 7995 tends to pull ahead in most benchmarks. And though it's not really intended for server use, if you have an application like Microsoft SQL Server that can be licensed on a per-core basis, there are arguments to be made for having fewer but more powerful cores. Let's have a look at the OEM machines. The first is the HP, and it's a no-nonsense workstation for any productivity task you face that has a major hunger for CPU. Perfect for software developers working on large projects, the HP was able to rip off a full Linux kernel compile in just under 25 seconds. If you're working on a project where multiple files can be compiled in parallel, the HP Z6 G5A workstation shines. This one came equipped with 128 gigabytes of memory, enough for most things, but a bit low for larger software projects like Chromium, as we'll see later. Now this HP, at least as it was spec'd for our evaluation, sports an RTX A4000 professional GPU. Now, that would be plenty for most video editing tasks, and for reference, the A4000 scored 130,000 points in the Geekbench GPU test versus a score of 227,000 from my trusty RTX 4080. The A4000 GPU score places it about on par with the M1 Mac Ultra Studio. The HP mustered a best of 10,936 in the Cinebench R24 GPU test versus a score of 21,489 from the RTX 4080. In Cinebench R23, it managed to muster a solid 100,000, a feat unimaginable just a year or two ago. High-end OEM workstations often have exquisite build quality, and the HP is no exception. Everything is toolless, and that extends from simply opening the case to replacing PCIe cards or accessing the RAM or even the CPU itself. Inside the HP, we find 8 sticks of registered ECC server memory running at 5,200 megatransfers per second for a total of 128 gigabytes. That A4000 GPU features 16 gigabytes of RAM, but the machine can be ordered with anything up to the A6000 Ada with 48 gigabytes each. Turning now to the Dell workstation, we find the same level of build quality and elegance in its internals. Access to the machine is again through a toolless side panel and everything is easily accessible. The Dell also features 128 gigabytes of its potential 1 terabyte maximum, but it's at a slightly lower clock rate of 4,800 megatransfers per second versus 5,200 in the HP. And while it's hard to believe, this Dell 7995 CPU with its 96 raging cores almost takes a back seat to its GPU configuration, because this workstation is built out as an absolute AI powerhouse. With its dual A6000s, this Dell is ready for pretty much any advanced AI workload that you can throw at it. Now, I wasn't about to train up my own large language model, but I needed some way to put the big GPUs to the test. Since SLI gaming is no longer part of the NVIDIA feature set, whatever software you're interested in needs to be specifically crafted to take advantage of multiple GPUs, and that can be a bit tricky as it's not an incredibly common setup. More advanced software like DaVinci Resolve should be able to leverage the 96 gigabytes of video RAM and all of the CUDA cores spread across the cards. While benchmarks typically do not use multiple GPUs, the new Cinebench R24 is an exception to that rule as it readily detects and makes use of both GPUs during a full rendering pass. And spoiler alert, the Dell with the dual A6000s is definitely the peak of the power curve for anything graphics or AI related, at least for the machines that I've ever tested. It scored an incredible 57,829 in Cinebench R24 versus 27,000 when just equipped with a single card. For reference, the 4080 mustered a best score of 21,489 and the A4000 in the HP managed 10,936. That makes the Dell almost 6 times faster for AI-dependent tasks than the HP, but that huge difference is really attributed to the GPU spec that the manufacturer opted to include, not knowing what the other ones would include. So had the HP been spec'd with the dual A6000s as a build time, it would have been an interesting showdown in that sense, but it wasn't. Still though, I wanted to put the AI and the GPU compute power of the Dell to the test by doing some actual work and not just running benchmarks. So to that end, I first tested crypto mining just to test the speed. Now, I haven't actually mined Bitcoin since the S3 ASIC was cutting edge, and so it's just not something I do anymore. But it's still a great way of testing the ultimate computation and memory accessibilities of your setup, so for a brief few minutes at least, I ran NiceHash to see how it would fare. And I was not disappointed, with the machine consuming over 600 watts of GPU compute power and producing hashes at a rate of 215 megahashes per second, which is quite impressive. I have no idea if it's profitable, but it's impressive. Next, I set up Stable Diffusion to do some AI image generation on the Dell. It cranks out images a solid 4 times or more faster than the A4000 and produces images in about 5 seconds at the default settings, so very convenient. The GPU power is impressive to be sure, but it's really the CPUs that brought us into the tent today, so the question is, what kind of tasks can even begin to make full use of 192 processing threads? Naturally, they always give you the complex-sounding but ambiguous tasks like big data and scientific simulation, where nobody gives you any specific concrete examples. But there are jobs like 3D architectural design where more CPU cores are easily leveraged. For tasks like machine learning, where you might suspect the GPU is the king, it's still up to the 96 cores of the GPU to keep the 16,000 cores of the GPU primed and running, so both serve an important purpose. A more prescient question might be to ask what someone like me can do with a CPU like this, and the answer is compile code. I grew up waiting for code to compile, and it's a little scary to guess at how many cumulative weeks, months, and years I've spent waiting for code to compile or assemble across the span of my career. In the old days, I used to smoke, and as projects got larger and larger, I'd have to switch to king size in order to just have enough time for my code to finish compiling.
Are you smoking yet?
The faster the machine can compile, the less time I spend waiting around, and the 7995s compile like beasts. The secret sauce when it comes to taking advantage of big core CPUs is to have a lot of work queued up that it can work on in parallel. A task like compiling lends itself easily to a large CPU because each C file, for example, can be compiled independently normally. Since a project like the Linux kernel contains about 30,000 C files, those can easily be distributed to the 192 threads, and there will be plenty of work to keep the CPU fully engaged at all times. That's true up to about the linker stage at least, where single-threaded performance then becomes the most important aspect. Until just recently, compiling the Linux kernel was a process that was measured in how many minutes it took to complete it, or how many times you could do it per hour. But with the 7995, we must now resort to measuring in seconds, because the HP ripped off a full kernel compile in 25 seconds, and the Dell did it in 23. Both times are impressive when you consider it's building some 30,000 files. But for even larger projects, the massively parallel nature that this chip brings with you can place high demands on system RAM. After all, you can easily run a C compiler with 128 gigabytes of RAM, but what if you're running 192 copies of that compiler at the same time? Each instance now has access to less than 1 gigabyte of RAM, and some days that's just not enough. For example, the Chromium source base is much larger than the Linux kernel, and on a really fast machine like these, it can take on the order of a half an hour to build. The problem becomes the RAM, since there just isn't enough RAM to build the Chromium source code at maximum speed in parallel all at once. Left to its own devices, the compilation would just run out of memory and fail, and so I tried to reduce load on the system by limiting the maximum number of threads. That got it to complete a build, but it also meant I wasn't using all of my cores. What surprised me the most was that using fewer cores didn't really slow anything down. In fact, building the code on 64 cores was about the same as 96, and I believe the reason comes back to that 350 watt chip limit. If there's already 350 watts of work to do, you can't add any more, as the chip can't process it within its stock power limits. To really put this theory to the test, I brought up Prime 95, and I tried running it on just 64 of the 96 cores, but even that immediately pegged the CPU right to its 350 watt cap. That made me question whether those additional cores, without the power limit to back them up, actually make sense at all. I decided to reduce it further to see how low I had to go to dip under 350 watts, and so I dropped the core count to 32, but it was still maxed on power. It was only when I dropped the core count to a mere 16 that the power finally bobbed down just under to about 330 and back up to 350, showing me that I was right at the limit. But only 16 of my 96 cores were engaged to do it. Now, I'm not a CPU expert, and I haven't read microprocessor reports since branch prediction was a new thing, so it's been a while. But I'm almost morally convinced of this point that many of the CPU cores will often go unused at the stock power limits because there simply isn't the juice needed to push computation through all 192 threads at once. And that's when I decided that I needed to know what this chip was really capable of if I could uncork it. And so I decided to build my own Threadripper, one where I would own it and could risk unleashing its full potential. The Threadripper chips actually set a fuse internally to keep track of whether the chip has ever been overclocked, and it will remember that forever. Now, AMD has not been denying warranty claims or anything based on it, and I highly doubt they have any objections to their own PBO performance mode, but it's something to keep in mind if you plan to tweak clocks and voltages on your own. When I set out to build this machine, I already knew that the CPU was going to be expensive, but I wasn't prepared for how pricey the ancillary parts would be. You see, there are two variants of the Threadripper, known as just Threadripper and then Threadripper Pro. That if you want the ability to run a Pro CPU like the 7995, then you need a motherboard that can support it. Your choices are quite limited, but thankfully Asus has a great board in the form of the WRX 90E. It features 7 PCIe 5.0 x16 slots, dual 10 gigabit LAN ports, 4 M2 slots, 2 rear USB 4 40 gigabit Thunderbolt style ports, as well as slim SAS NVMe support. With 7 slots, each featuring full x16 connectivity, you'll never despair for PCIe lanes again. It also supports full remote management with an onboard AST2600. All those features aside, however, the next most surprising thing about this board is its heft. The board alone is 12 pounds, which doesn't sound like a lot at first, but if you think about that in terms of throwing around a 10-pound dumbbell and then you realize that that's lighter than this board, it gives you some context of what it's like to hold it up in place as you start the first screws. It's a monster of a board with equally monstrous VRM power and cooling to support overclocking of the 7995. Now again, when I say overclock, I'm really just turning on PBO and telling the board to use the VRM power limits and not those built into the CPU. The CPU will then use all the power it can get, subject to its ability to stay cool and within the right clock rates. But we won't be tweaking clocks or voltages or anything like that, just PBO. My first tests with the Asus board were both exciting and disappointing. Exciting because I could see the CPU was pulling over 1,000 watts on the first hit of the throttle, but it would then quickly drop off and settle down to around 600 to 700 watts. Now, it's still double the original power limit, however. But don't be confused into thinking that everything is going to be linear here. It's not going to get twice the work done at 700 watts that it did at 350, but the increase is still significant. For a cooler, I read all the reviews and I watched all the videos, and the consensus seemed to be either the Arctic Liquid Freeze or the Asus LC2 Strix Pro. I figured I was using an Asus board, so I'd go with the Asus cooler, and indeed, it turns out to be a high-quality 360 AIO powered by the same Asustek pump that everybody seems to be using these days. For better or worse, I could never get their RGB software to work without crashing, but didn't really care, and the pump and cooler otherwise seemed up to the task, at least from my inspection. For a PC case, my choices were equally limited. This main board is a larger variant of the EATX form factor, and the only two cases I was confident that it would fit would be the Fractal Design 7XL and the Lion Li V3000 Pro. As a longtime Lion Li fan, I went with the latter, and it's a great case. The only problem with it is that it's so large internally that you might have issues with longer power cable runs. But with the Seasonic 1200 watt power supply that I selected though, everything reached, though just barely. Even before I had the motherboard assembled in the case, I threw it together on the bench to do some initial bench testing. Now, the HP and the Dell were both able to break the 100,000 mark in Cinebench R23, which is already quite impressive. And at the sustained power levels that I was now seeing, the score pushed its way up and over 120,000. The problem was now cooling, as the chip would immediately hit its 95 Celsius thermal limit and stay there the entire run. I just couldn't get the heat out fast enough, it seemed. Now, I was running the 360mm version of their cooler, and then I discovered they also make a 420, but I didn't think that the radiator was actually the limiting component. I used my thermal camera to inspect the system, and I could see that the water running into the water block was 20 degrees cooler than the water that was leaving, and that very little heat was coming off the third radiator fan. So to me, that signaled that the radiator part of the equation was up to the task, and so that left the pump and the water block as potential culprits. Since the pump and the water block are an integral unit, changing either means a whole new AIO, but how would I know that that was my issue? It's largely because the Asustek water block that contacts the CPU is too small, and you can see that much visually. The little circular contact area looks to be about 2/3 of the total area of the heat spreader on the Threadripper CPU, and so a lot of the CPU is just exposed to ambient air and is not actively cooled by the water block at all. So what I really needed was a water block specifically designed for the TR4 socket. The 7995 chip actually comes with a pump bracket just for this purpose, but it's only intended for that small common pump. So to get some better coverage, I did some more research and found water blocks intended for the TR4, but they're all made for use with a custom water cooling loop. And quite frankly, even though I've been a plumber for many decades, I just didn't want to bend pipe, nor did I want to risk a $10,000 CPU to the prospect of a coolant leak if I made some silly mistake. So what I really wanted was a self-contained AIO with a TR4 water block. And fortunately, I was able to find one made by Enermax, and so I ordered one and swapped it in. The improvement was immediate and obvious. While it would start off at 1,000 watts and again fall off a bit from there, now it would settle down between 750 and 900 watts of sustained power, a far cry from the 350 watt stock levels. Now that the cooler covered the entire chip, it was able to carry heat away from the source much more effectively. I also made one significant improvement over the way the OEM machines were spec'd in that now I upgraded to 512 gigabytes of RAM, hoping that would allow the Chromium compile to complete in parallel. And this is where you really start to appreciate the reliability and dependability of the OEM setups, as everything is pre-engineered to work together in a rock-solid manner. My new system was anything but. It would crash, but not right away. It would take 10 or 20 minutes of running at maximum load, and then it would spontaneously reboot. And sometimes it wouldn't come back up at all, and I'd have to do a complete BIOS reset and start over. It turns out that although the RAM I purchased is actually rated at 5,800 megatransfers per second, I wasn't able to get it to run in a stable fashion beyond about 5,200, the same as the HP. So I spent a lot of time running within the paper spec, only to have the machine constantly reboot until I tamed that spec down a bit. So if you absolutely, positively need the additional performance that unlocking the chip can bring, I suppose the smart compromise might be to purchase a system from somebody like Puget Systems, who will pre-test and vet the config so that it works when you receive it. You'll pay a premium for that service, but if you need the performance that an OEM system can't provide, it's probably your next best option. As for me, however, after a couple of days of testing and tuning, I had the system in an apparently reliable state, so it was time to do some performance testing. Let's have a look at how the system stacks up against these stock options. Looking at openbenchmarking.org, I was able to see that the very fastest 128-core EPYC chips were capable of building the Linux kernel in as little as 20 seconds, which seemed to be the record. I fired up the compiler and almost immediately beat that at 19 seconds. Compare that to about 25 seconds on the OEM systems. Soon enough, it came time for the Chromium compile, where it could really put the system to the test. And if it survived a full half hour at maximum load and heat soak, I could be reasonably confident that the machine would be stable. This took several tries and several days, and it's just one of those things that just works when you buy an HP or a Dell or an OEM system over trying to piece things together yourself. With the cores limited to 128 so that it could survive without running out of memory, it took the Dell 32 minutes and 30 seconds to build Chromium. On the Beast machine with 512 gigabytes and the CPU running in the stock config, that came all the way down to just over 20 minutes. Turning on PBO brought us down to 17 minutes and 30 seconds. And then changing over to the Enermax cooler brought the best and final time down to 16 minutes and 54 seconds, coming close to cutting the total build time in half. And that's when you can see the true power of an unleashed Threadripper in its rawest form, when it's allowed to run free and eat. What? And that's when you can see the true power of the Threadripper in its rawest form, when it's allowed to run free and unleashed. And should you ever be tasked with the problem of having to spec out a top-tier Threadripper for yourself, which way you go is really up to you and what matters most. If you're buying a machine that costs $20,000, you might rightly believe that only the most rock-solid solution is anything like acceptable at that price. On the other hand, you might be of the hot rodder opinion that for that kind of money you'll compromise on other things but not performance. Ragged edge fast or rock-solid reliable, pick either one. Either way, the 7995WX is sure to impress. Among the OEM systems, the HP is slightly faster than the Dell due to marginally faster RAM, but otherwise, your performance will really be determined by your pocketbook and how you choose to equip your system at checkout. If you found any of today's episode to be interesting or entertaining, remember that I'm mostly in this for the subs and likes, so please be sure to leave me one of each before you go today. Please consider turning on all notifications for the channel so that you don't miss an episode. And if once a week turns out to be too often, you can always turn it back off. If you or someone you know may be on the autism spectrum, check out the free sample of my book on Amazon. It's everything I know now about living your best life on the spectrum. Thanks for joining me out here in the shop today. In the meantime and in between time, I hope to see you next time, right here in Dave's Garage.